everybody, and welcome back to another video. I'm sorry that it's taken me so long to take this out. I had winter break in the Christmas season, which was very busy, and today I just finished up my first week of school back. But I'll be back to making videos for you guys now, so don't you worry. Today I want to talk about probably the last topic we'll cover for integration, that being partial fraction decomposition. Partial fraction decomposition, that's a lot of really big words, and it's definitely a mouthful. But I mean, what does it actually mean? What is it? Well, the idea behind partial fraction decomposition is this idea, that if you have, say, x times y, that can be two numbers, or it can be two expressions, which is how we'll be using it later. If you have two expressions multiplied in the denominator, then you can split it into two separate fractions of some expression. Usually it's called a over x, and then plus another expression, we usually call it b over y. So you see we have x times y here, and it splits that problem of multiplication in the denominator into being just adding the two fractions here. So I'll go over how you can find exactly what a and b are, and then how they're actually used in integral calculus. First up, I'm going to make sure that you are comfortable with solving integrals with the expression of x in the denominator, all right? Now, if you remember from previous videos, we know what the derivative of the natural log of x is. The derivative of the natural log of x is 1 over x. So, since the integral is also the antiderivative, if we want the integral of 1 over x, we're going to get ln x, natural log x. Okay, perfect. So this is going to be, but it's not 1 over x, is it? It's 1 over x plus 1. So what the heck? This is where we employ a u substitution. So if we let u equal x plus 1, and then we differentiate both sides with respect to x, we'll get that du dx is equal to just 1. This means that du is equal to dx. All right, well, what does that mean? It means that we can change the integral into the u world. Since du is equal to dx, we can change them just without any precautions necessary. And we said that u is equal to x plus 1, so we'll just put a u there instead of an x plus 1. And now we do have that pattern that we were looking for. We have 1 over a variable. And so we can just say that this integral is equal to the natural log of that variable. Now, of course, we want to be in the x world for our final result, so we'll just translate back. If u is equal to x plus 1, then we can just plug in x plus 1 right here, have our plus c, and we're done. All right, this is the answer for this integral. Why did I show you that? Well, let's get into what our topic is today, being partial fraction decomposition. How about we try this integral? Now, this integral is very different. As we see, we have an x squared term, so we can't just do the same thing we did last time. But what we did see last time is that if we can get it in terms of integrals with just a linear term in the denominator, then we can just use a u substitution and we can find the natural log solution for it. So that's the goal. We need this to become a sum of expressions with linear terms in the denominator rather than this x squared quadratic term. So how do we do that? Well, the first step is going to be to rewrite it 1 over x squared plus 3x plus 2, a little exercise in polynomial factoring, but this is going to be x plus 1 times x plus 2. And we still have our dx. Okay, so maybe we do a u sub from here, but that only worked in the last one because we only had one term in the denominator. This time we've got 2, so we're going to have to pull out the technique I've been talking about. So we are going to be using this trick. Our expression is 1 over x plus 1 times x plus 2. So the two expressions being multiplied are these two linear terms. So we're going to have a over x plus 1 plus b over x plus 2. Well, what the heck are a and b? How is this going to help us? Well, here's what we can do. If we multiply both sides of this equation by x plus 1 times x plus 2, so multiplying by both at the same time, this will cancel and this will cancel, and we'll be left with 1, right? If we multiply 1 over x plus 1 by x plus 1, it'll cancel. Same thing with x plus 2. If we multiply it by x plus 2, top and the bottom, it'll cancel. So 1 equals. Now, with this a term, since we're multiplying it by x plus 1, that term will cancel, So we'll be left with an a, but we still have an x plus 2 that we're multiplying by. So this is left over. And it's similar with the b term. The b is left over as the x plus 2 will cancel, but an x plus 1 is left over. Okay, well still, this is 3 different variables. I mean, come on, what are we doing here, right? How does this help us? Well, since x is just any number, we can choose specific numbers that'll help us find what a and b actually are. So to do this, we always set the inside of one of these to be 0. Okay, well, how do we do that? X plus 2 is equal to 0. I'm sure if you're taking calculus, you can do that in your head. X is equal to negative 2. So we'll set x equal to negative 2 and see how that affects our equation. We get 1 equals a, we get 0, negative 2 plus 2 is just going to be 0, plus b times, well, negative 2 plus 1 is just negative 1. All right, so this is our expression. But a times 0, well, anything times 0 is just going to be 0, so that cancels out. So we get that 1 is equal to b times negative 1, or that 1 is equal to negative b, and I'm sure you can figure out what b is from here. B is equal to negative 1. All right, great, so we know that. So now we go back. We know that b is negative 1 already, so we can replace that up here. And now let's solve for a. Now to solve for a, we're going to have to make this part equal to 0. X plus 1 needs to be equal to 0. X is going to have to equal negative 1. So x equals negative 1. Let's see what we get. 1 comes down from this side of the equation. A times negative 1 plus 2 is 2 minus 1. That's just 1. So we're just going to get a left over. And then plus b times, well, x is negative 1, so we have negative 1 plus 1. 1 minus 1 is 0, right? It goes away, it cancels, and we're left with 1 equals a, or a equals 1. So now we can put that up here. So we get this expression. 1 over x plus 1 times x plus 2 is equal to 1 over x plus 1 plus negative 1 over x plus 2. All right, well, since these two things are equal, we can substitute it here inside of our integral. So what we end up getting is this integral of 1 over x plus 1, and then instead of saying plus negative, I'm just going to say minus 1 over x plus 2. Now this becomes much easier because since we're subtracting within the integral, we can just take the difference of the integrals. So we'll integrate 1 over x plus 1 minus the integral of 1 over x plus 2. All right, well, we already did this basically. What we're going to get is the natural log of these denominators, since you can just do a u sub, and then the antiderivative of 1 over a variable is the natural log of that variable. All right, so let's do that. So this was our expression, the integral of 1 over x plus 1 minus the integral of 1 over x plus 2. So applying the strategy I just talked about, we get the natural log of x plus 1 minus the natural log of x plus 2, and we can add on our little plus c at the end here to make sure we've got the full answer. So this is the entire idea behind partial fraction decomposition. It allows you to take any polynomial which is greater degree, and then if you can factor it, you can split it into different fractions that are much, much, much easier to deal with, because it's just pretty much one step if you just skip the in-between of the u sub. Now, this is super convenient, but it isn't technically the only method of solving integrals like the one I just showed you, but it is by far the easiest, in my opinion at least. I don't know anyone that would think differently. But anyways, hopefully you're able to understand what's going on. If you guys want another video where I go over more examples, let me know in the comments. But for now, thank you so much for watching.